Negative number representation. There are three common ways to represent signed numbers in digital systems. These are the sign and magnitude notation, the ones complement notation, and the twos complement notation. In the sign and magnitude notation, the negative numbers are usually written in the ending minus sign in front. You see, this is a negative 12 in base 10, and we have a minus sign in front of it. This is a negative number in base 2, and we have a minus sign in front of it. In computers, we use the first bit to represent the sign. 0 is a positive number, and 1 is a negative number. The most significant bit of the number used to represent the sign of the bit in this notation. So if we have an 8-bit number and we want to represent it in sign and magnitude notation, the first bit, which is the most significant bit, is this bit, is the sign bit, and the rest of the number is the magnitude, 7 bits. So in this 8-bit number, the largest positive number is that has the sign as a 0, and the rest of the numbers are ones here. And this actually is plus 127 in base 10. This is a positive number. The largest negative number, this bit is 1, while the magnitudes bits are ones. So this is a negative 127 in base 10. The 0 has two representations in this notation. We have a positive 0 and we have a negative 0. It's not good to have two representations for the same number. So the range here is from minus 127 to plus 127. If we are talking about an 8-bit number, in this sign and magnitude notation. To negate a number in this notation, suppose we have this number, all right? To negate this number in base 2 by putting a minus sign in front of it, all you have to do is inverse the sign bit. So this is the negative number for this number. The same thing here, they have a number. To negate it, all you have to do is inverse the sign bit, and you get the negative number of this whole number. Okay, the second representation notation for the negative numbers in digital systems is using the ones complement. What is the ones complement of the number? This is a binary number, and we know that digital systems, they have numbers as binaries, as zeros and ones. Okay, the ones complement of this number can be found by inverting the bits, inverting each bit. So this is inverted to 0, and the new number that comes out is this. So this is the ones complement of this number. For this number, the ones complement is you invert each bit, and so on. Actually, you can find the ones complement of any number. For example, given that you have an 8-bit number, which is this, what is the ones complement? It's either you invert each bit and you get the ones complement, which is 1, 1, 0, 0, 1, 1, 1, 1. Or you can use this formula to find the negative number of x. 2 to the n. N is the number of bits here, which is 8. 2 to the 8, which is 256, minus the number. The number is 12, minus 12, minus 1, minus 1 in base 10. So that's 243 in base 10. Convert the 243 into binary. What do you get? You get this number. So this is the ones complement for this number, which is the same as we found earlier here. Now that we know how to find the ones complement of the number, how do we represent the positive numbers in ones complement? The positive number in ones complement, we treat them as sign magnitude notation. For example, this is a positive 14 in base 10. 14 is this as an 8-bit number, okay? And the ones complement for this number as a positive number is the same. We invert nothing here. So this is the positive 14. Negative 14, okay, which is negative, and this is the binary number, okay, we take the ones complement. We take the ones complement, we invert each bit. So this number is a negative 14 in ones complement. This number is a negative 14 in ones complement. If somebody tells you that this is a negative number and it is your system is using the ones complement, and you want to find the absolute value of this number, all you have to do you know that this is a negative number, okay? Invert and find the ones complement of this, which is 0, 1, 1, 1, 0, 0, 0, 0. So this is a negative 14. This is 2, 4, 8. Add them together, you come up with the 14. Okay, if someone tells you that this is a number in ones complement notation in your digital system, what is the value of this number? You know that this is a positive number, okay? And positive numbers in ones complement are the same as sign magnitude. So the value of this is positive 127. Positive 127. This number is a negative number. So if you want to find the absolute value of this number, you have to take the ones complement for this number. The ones complement for this number is 7 ones and a 0, and this is equal to 127. 127. So this number represents minus 127. The 0 can be represented as a positive 0, as a negative 0. It has two representations, because if you look at this number as a ones complement, this is a minus, and then you take the ones complement for this number, which is 7 zeros, so this is a minus 0. So the range for an 8-bit number in one's complement notation is from minus 127 in base 10 to plus 127 in base 10, and the 0 has two representations, just like the sign magnitude notation, and this is not good. Third method to represent sign numbers in digital systems is using the 2's complement notation. What is the 2's complement of the number? The 2's complement is the 1's complement added by 1. So if we have this number, the 1's complement for this number is this one. Okay, if you add 1 to this, you get the 2's complement. 1 plus 0 is 1. And here you have 0. 0 plus 1 is 1. So this is the 2's complement for this number. So the 2's complement is the 1's complement plus 1 for the number. For example, this number. What is the 2's complement for this number? You find first the 1's complement. This is the 1's complement for this number. And then you add 1 to it. So what do you get after you add 1? 1 plus 1 is 0. And 1 here. 1 plus 0 is 1. And the zeros go down and the 1 go down. So this is the 2's complement for this number. I'll tell you another way to find the 2's complement. Okay, you start from the right here and go this way until you find the first one. Keep these 2 bits as is. Okay, and invert the rest of the bits as you see here, and you will get the 2's complement. Another way to find the 2's complement, for example, we have an 8-bit number, which is this. This is a 14, 8-bit number. The 2's complement of this number is 2 to the n, where n is the number of bits, 2 to the n, which is 256, minus the number. The number is 14. I'm sorry, in this case, the number is 12. So 256 minus 12, that's 244. Represent this in binary, you get this, 244. Okay, if you apply what I told you before, you take these 3 bits with no change on them, all right, and then you invert the rest, you get the 2's complement. In 2's complement representation, the positive numbers, they stay the same. For example, this number plus 14 in base 10. This is 14 as a binary number. This is a plus number, so it stays the same as the binary representation, as the sign magnitude notation. Notice that the first bit here is 0. That means this is a positive number. However, the negative numbers, okay, this is a negative binary. So this is put in the 2's complement notation. So we have the 0, 1 here, and the rest are inverted. The rest are inverted. So this is the negative 14. When we see that this bit is 1, to tell you that this is a negative number. If you want to find the absolute value for this one, you have to take the 2's complement for this one. What is the 2's complement for this one? It is 0, 1, 1, 1, and 4 zeros. Okay, so this is a negative, what? A negative 14, which is this. In 2's complement notation for sign numbers, what is this number? This is a positive number, right? And this is the absolute value of the positive number, which is 127. This is for an 8-bit number. What is the value of this one? This is a negative number. Okay, a negative number. What is the value of this negative number? You have to find the 2's complement for this number. The 2's complement for this number, you go to the right until you reach the 1. So the 2's complement for this number is the same as the number itself. Okay, so what is this number? The weight of this one is 128, which is this. So this is the smallest number in the largest negative number in an 8-bit number. The 0 has only one representation. Okay, it's a positive 0. We have no negative 0 in this format if we're using 2's complement. And this makes it a good number to use in digital systems. So for an 8-bit number, the range is from minus 128 in decimal to plus 127 in decimal, and the 0 has one representation. So this number is the best among the three to represent signed numbers in digital systems. Notice that in this system, as in the other systems, the most significant bit represent the sign. Plus is represented by a 0, and minus is represented by a 1, just like the 1's complement notation and the sign magnitude notation. Let's see how we can represent 4-bit sign numbers in the sign magnitude notation, in the 1's complement notation, and the 2's complement notation. Let's take the positive values first. In 4-bit sign numbers, the positive values range from plus 0 to plus 7. In sign magnitude notation, the plus 7 is 0, 1, 1, 1. You notice that the first bit here is 0 to indicate that this is a positive number. And this goes actually for all the rest of the numbers. Okay? And the values for each number, 111 is actually 7. 111 is actually 7. This is a 1, this is a 2, this is a 4. Add them together, you come up with 7. Okay, plus 6 is represented in this system as 0110. This is the absolute value, which is 6 in binary, and this is a positive 6. The same thing for plus 2. This is the 2 in binary, and this is the positive value. Okay, in the 1's complement notation, okay, the positive numbers are expressed as the same as in sign magnitude notation. The first bit is the sign bit, which is always, in this case, equal to 0, and this here is the magnitude of the 7. Okay, this here is the magnitude of the number 4. The same goes for the 2's complement notation. Also, the 0 here indicates a positive number, and these are values for the absolute number. Okay, this is number 3, positive 3 in 2's complement notation. The negative numbers for a 4-bit signed number. For a 4-bit signed number, the negative numbers are from 0 to minus 8. In sign magnitude notation, this is a minus 0. This here is the sign bit in all the numbers. Okay, and this is the value. Minus 5 is represented as minus 4 plus 1, which is 5. In 1's complement notation, okay, the negative number is the first complement of the positive number. The positive 0 is 4 zeros. So the negative 0 is the complement, the first complement, which is 4 ones. Okay. This is the number 2, 0, 1, 0, 0 as a positive 2. The negative 2 is the complement of that, which is 1 here, and 0, this one, and 1, and 1. So this is a negative 2. Again, this here indicates that this is a negative number. Okay, let's take this example. The plus 6 is 0, 1, 1, 0. Okay, if you want to represent this in ones complement notation, you put it in the ones complement notation, which is 1, 0, 0, 1. Exactly as this. Okay, in the twos complement notation, we take the twos complement of the number. Let's take the positive 3, for example. This is a positive 3, 1, 1, 0, 0. The negative 3 is the twos complement of this number, which is 1, 0, 1, 1. All right, which is this. Suppose we have this, given the following number in twos complement notation. You are given this number in twos complement notation. Find the decimal value for this number. You take the twos complement of this number. From the start, you should notice that this is a negative number. So to find the absolute value for it, you take the twos complement of this number. Then you find the values for the ones here. Okay, this one has a weight of 64. This one is 32. This one is 16. This one is 2. And this one is 1. You add them up together and you come up with 115. So this number actually is a negative 115. I can do this in a different way. All right. The weight of this one is 2 to the power 7. And this is a negative number, so this has a value of minus 2 to the power 7. All right, and this is 2 to the power 3, and this is 2 to the power 2, and this is 2 to the power 0. If I add them together, this one here is minus 128 plus 8 plus 4 plus 1 equal to minus 115, which is the same answer I got here. Okay, let's take another example. This number is given and it's in the ones complement notation. What is the value for this number? Of course, you notice that this is a negative number in ones complement, so we take the ones complement for this number. And then we put the weights for each bit of the ones and we add them together. So this number is equivalent to minus 114.